Hi guys, so welcome to the first video in a series of lectures covering fluid mechanics. So we'll be starting off with dimensional analysis. Then once we're through with this, the goal is to be able to solve dimensional analysis questions either through Buckingham's Pi method or through Rayleigh's analysis, depending on how the question may come about. But we'll start off with a conceptual introduction. That's what we're doing here. And as we go on, we'll see how dimensional analysis comes into play. Okay? So why should we care about dimensional analysis in the first place? I have a very cool illustration for this as to why dimensional analysis is important. Okay, but you're going to have to imagine with me for a minute. Let's say we're tasked with finding a formula for the speed of the boat. Okay, so let's say we have a boat in some body of water and we're looking for the speed v. Okay, v question mark. What's the speed of this boat? So you could say, all right, since we plan to be driving it forward. Okay, someone is here driving the boat forward. So let's say the boat moves forward with an initial speed u. Okay, so what else could affect the speed of this boat? You can look at the sail and say, all right, wind speed. So let's call that w. The net direction of the wind will affect the speed of the boat. Then we look at water and how this can affect. We said, okay, the heavier the boat, the slower we expect it to move. So let's call this mg for simplicity. Okay, when a fluid, so we definitely have upthrust. So let's say upthrust, we can call this capital U. And we're dealing with two surfaces. So we also definitely have to deal with viscosity. So let's call this mu. Okay? This is just to simplify it. And what else could affect the speed of this boat? There could be friction between the transmission and the rotor blades at the end. So let's call this internal friction F, and so on and so forth. So coming off from scratch with an equation for the speed of this boat, we'll have to take 1, 2, 3, 4, 5, 6 variables into account. And the way this is done is that we'll keep everything constant and vary one. So let's say we keep everything constant and vary the wind, get our values for those, keep everything constant and vary the weight of the boat, get our value for those, and be able to see if we can magically come up with a relationship with 6 different unique table of values. But the advantage we now have with dealing with dimensional analysis is that we reduce the number of independent variables, usually from 6 to something like 3 or 4, or sometimes even 2, okay, depending on the parameters of the situation. So once you now have less variables, you're able to come up with a simpler way to experimentally determine whatever it is you're trying to generate an equation for. So that's just to give us an idea before we start off of what we stand to gain when using dimensional analysis before we get into the main definition. So we'll definitely see that being more explained as we get on in solving problems. So let's go. What's dimensional analysis? With a question mark. Dimensional analysis is the study of the relationships between physical quantities and their dimensions. Okay? In simpler terms, dimensional analysis helps us understand physical problems by looking at the fundamental building blocks of the quantities involved. Okay? So let's say we know things are made up of, we describe things by units, by dimensions. So let's say we've got speed. So we're trying to look at energy. So kinetic energy, okay? So energy, K for kinetic. So this may depend on speed and mass, okay? Since the formula for that is half mv squared. All right. So dimensional analysis will now help us study the relationships between these physical quantities through their dimensions. Okay. So we know mass is in kilograms and speed is in, let's say, meters per second. But these are units. But as we get on with this, we'll now come to understand the difference between units and dimensions and how they help us to solve problems. So it helps us understand physical problems by looking at the fundamental building blocks of the quantities involved. If you remember the hypothetical example we gave earlier, it helped us to understand the physical problem of evaluating the speed of the boat by looking at the building blocks of the quantities involved. We looked at wind, we looked at weights, we looked at viscosity, and so on and so forth. All right. So that is just what dimensional analysis is. It helps us look at, okay, I have an expression for something. What dimensions are the components of my expression made of? Okay. So as we go on, it will definitely make more sense and it's become easier for us to solve questions on this. So just to establish for theory purposes, what are the applications of dimensional analysis? So it helps us to check dimensional homogeneity. So I'll link the video to this at the top over here. Dimensional homogeneity is the principal concept behind dimensional analysis, okay? So it helps us to say that, let's say we have a formula, y is equal to a plus bk plus root c, okay? Dimensional homogeneity tells us that every term in this expression, since it's a sum of different products, should end up with the same units, same dimensions. So let's say the dimensions of a are ml, dimensions of bk should also be ml, and dimensions of root c should equally be ml for the principle of dimensional homogeneity to hold. But we'll definitely get more in-depth into this in the next video, but that's just for theory purposes. It helps us derive relationship and formulae, as we covered that, and it helps us to create dimensionless groups. So when we deal with Buckingham's Pi theorem, okay, so Buckingham's Pi theorem, okay, we'll now learn what it means to be able to create dimensionless groups or pi groups. Okay, so these are combinations of variables in equations that have no dimension. They're dimensionless, like constants. But that's good for us because it will help us create the relationship or formulae that we're looking for. And lastly, it helps with model testing, like we said before. So to hold controls for experiments, dimensional analysis helps you reduce the number of independent variables you have to keep constant and you have to toggle so that experimentation is easier at the end of the day. Okay? The key advantage is that it reduces the number of variables involved in any expression, making it easier to test. So we covered this before. So now let's look at something very important that will cause a stumbling block that's very likely to cause a stumbling block as we carry on in this series, okay? Dimensions versus units. So I'll start with a bit of a definition. A dimension is the physical nature of a quantity. Okay, so let's write that down. Is the physical nature of a quantity. A quantity. While units, on the other hand, are a standard magnitude of the same physical quantity. Okay, so standard magnitude of the same physical quantity. All right, so what do we mean by this? We could have, so let's say we're trying to measure time. We're talking about time, for instance. The physical nature of time is going to be time itself. So we can call this capital T. But the units of time may vary. Okay, you've got hours, you've got seconds, etc., and so on and so forth. So I'm going to put a tables just so we're able to understand the difference between fundamental dimensions and the fundamental units for clarity's sake. Okay, so let's say the quantity is going to be on this hand, the dimension, and the units. Okay, so let's start length. So we'll start off with length. If you think of many units for length when we've been solving physics questions, you could have many meters, centimeters, kilometers, light years even. Okay, so these are all units for length, but the dimension is the spelling is wrong. Light years. Okay, but the dimension is the physical nature of that quantity, and the physical nature of each and every one of these is a length, simple and short. So we denote this with the capital letter L. Okay, usually with square brackets around this. All right, so units are instances of dimensions. Okay, there are different ways to sample a dimension. So let's finish this up first and we'll get into explaining that more in depth. So let's say mass. When we think of units for mass, you've got grams, kilograms, pounds, and so on, and tons, okay? And tons. So and so on and so forth. So these are different ways to sample mass, but the dimension for mass will always remain a capital letter M. And lastly, for time, as we covered before, you've got seconds, hours, minutes, etc., etc. But the dimension for this is going to be always going to be time. All right. So remember we said that units are instances of dimension. So let's say we're measuring a fundamental nature of our unit is length, right? We're looking at length. So this is representing a particular length. Units are, as we said, is a standard magnitude of the physical quantity. So centimeters could sample the length with short breadths like this, right? Each of a uniform referenceable standard. Okay, so these may be centimeters, then kilometers may be longer than this, but each of them repeatable and standard. It has to be standard for it to be a unit, but dimensions are constant and stay the same. So the same happens for mass, the same will happen for time. So that's what these are. I've also inadvertently introduced the three fundamental quantities. Oh, pardon me. Okay, the three fundamental quantities we'll be dealing with when handling fluid mechanics questions, especially dimensional analysis. Okay, but let's move on. Fundamental dimensions or units. Okay, there's 7 fundamental. Usually in an introduction to physics course, you will have to encounter this, but there's 7 fundamental dimensions or units. We've introduced the first 3: mass, length, time, and then we have electric current, temperature, amount of substance, and luminous intensity. So now you have to take note of something. The standard units, the SI unit, is the universal unit being chosen for whatever fundamental quantity we're trying to measure. So remember we said that we have a lot of, for lengths, we said we had centimeters, milliliters, decimeters, meters, kilometers, and so on and so forth, whatever astronomical units, okay? So whatever distance, whatever range of distances you can think of for sampling. So these are all different units, okay? But for standardization purposes, we need a standard of the standards. So that's what the SI units are. It's the International System of Standards, okay? So that of mass has been agreed to be kilograms. Of length is meters, okay? Time is seconds. Current is amperes. Temperature Kelvin. Amount of substance moles. And luminous intensity is the candela. Okay? So they're called fundamental units or fundamental dimensions because they cannot be expressed with each other. They are independent. There's no way you can express mass in terms of time. There's no way you can express temperature in terms of amount of substance or brightness in terms of currents fundamentally per se. But that's the idea. But for our fluid mechanics course, so what we're doing now, we'll only be concerned with these 3, okay? Mass, length, and time. And these are the 3 fundamental dimensions that we'll be dealing with for them. So you get more familiar with them as we see them in upcoming questions. All right. So deriving dimensions. Now we're getting to the really cool application part of all the theory we've been explaining since. So now the idea is to derive the dimensions for particular physical quantities. So the best way to do this is to start with a physical interpretation. Okay, so let's say you want to derive for velocity. You want to ask yourself, what is velocity? So now that velocity is a distance over time. So I can say is a length divided by time. Okay, so let's start off. Velocity. So I know that it's a length over time. Okay, and there are fundamental units for length, there are fundamental units for time, but since we're dealing with deriving dimensions, we have to remember that deriving dimensions, we now deal with the dimensions of them. So the fundamental dimension of velocity is going to be Remember that of length was L. Okay? It's L over T. Okay? And then in more, by convention, you could say LT raised power minus 1. So this is raised power minus 1 because it's the denominator of this. Okay? It's just to write it in one line and to keep it neat. So the dimension of velocity is LT minus 1. So whatever velocity you're going to end up with, whether you're dealing with centimeters per second or kilometers per hour, every one of them is going to have the dimensions of length per time. Okay, length per unit time, LT raised power minus 1. So as you go forward, so let's see, acceleration. Okay, so now we've got to ask ourselves, what's the physical interpretation of acceleration? Acceleration is the change of velocity over time. So you can start with the formulas, okay? So acceleration is, so let's say it's change in velocity over change in time, okay? So since these are changing, is technically velocity over time. So remember we just derived the dimensions of velocity to be LT raised power minus 1. So all we have to do is divide that again by time. So we have velocity divided by that of time, okay? So which would be the same thing as the units for velocity times time raised power minus 1, okay? Which would be, recall velocity is LT raised power minus 1. So LT raised power minus 1 times T raised power minus 1. So from the principles of indices, we can just add these two together. LT raised power minus 2. So it's the length per length per length, okay? So it's velocity over time. And we established that it's going to be LT raised power minus 2. No. So we established that it's going to be LT raised power minus 2. Next thing we have to handle, okay, is density. So let's ask ourselves, we start with the physical interpretation. Density, okay? Or you could start with the formula, whichever works. So density that's rho. Rho is mass over volume, okay? So I can write that as my physical interpretation. Density is mass per volume, okay? Mass is a fundamental unit on its own, so that's going to be m. So now okay, this is volume. So now we're going to ask ourselves, what's the dimension of volume? So know that area, a single length is length L, okay? When we're dealing with area, is length times length, which is going to be L squared. But if we're dealing with a volume, for instance, we're multiplying length 3 times, okay? So that's going to be L cubed. So a single length is going to be L, and area is going to be L squared. And volume is going to be L raised power 3, L cubed. So we're dealing with density, that's mass over volume. So rho is going to be, the dimensions of rho is going to be m over L cubed. So to simplify the indices, is m L raised power minus 3. Right? Yeah. Okay. So we can keep up the pace and keep going with this. So pressure is force over area. Okay. And I think we should do force first, then apply that to pressure. And force is mass times acceleration. Okay. So let's do for force first. So we know that F is equal to ma. Okay. The dimensions of m is mass, so that's going to be m. And a is acceleration, and we got that already. So that's LT raised to minus 2. Okay. So that means the dimensions for force is going to end up being m LT raised to minus 2. So it's important to know that this applies for it should apply for every single formula you have expressing force, gravitational force, electrostatic force. magnetic force is always going to reduce to this dimension. So that's why it's very important for us to make sure that the dimensions are conserved. Okay. And lastly, we look at pressure. Okay. So pressure P, you know that pressure is force over area. So that's force divided by area. We've gotten the units for the dimensions for force as ml t raised to minus 2. I know we covered that area is L squared. So let's do the division. Force is ml t raised to minus 2. And area is L squared. So that's going to be L raised to power 1 times L raised to power. Okay, so let's write this out. If we're to write this out, so you know we're dealing with pressure P. So our numerator is force. So that's ml t raised to minus 2. And we're dividing by area. So our denominator is going to be L squared. If we were to take it up, it would be times L raised to power minus 2. So that's going to be m. L is L. So from the laws of indices, if you're multiplying the same base, you add the indexes. So L is L raised to power 1, then minus 2. Okay? Times T raised to power negative 2. So that's going to be m. L raised to power minus 1, T raised to power minus 2. Alright, and so on and so forth. So these are the steps that we take when trying to derive the dimensions for a given physical quantity. You can start with the physical interpretation, and you can also get that from looking at the formula for such a problem. So that pressure is force over area. We got that for force. If we were to look at force alone, we'll get that for acceleration, since we have to get the dimensions of each component. Look at the physical interpretation, then perform the dimension operations that the formula requires to be able to end up with the dimension of the units. Okay? So it's very important to note, especially here, let's say here when we're dealing with density. It's that pressure, that's density, so this is rho, is mass over volume. Okay? And although we're writing m here as mass, we've got to make sure to not mix it up with m for meters. Okay? That's a very common mistake that happens when dealing with dimensional analysis. So that's why you try to keep your m for mass and as capital. And when handling meters, you can write that in full or keep it as small letters to be able to keep that in mind. Okay? So the dimensions of key quantities, we're able to do some of these ourselves. So velocity, the physical interpretation of this is distance per unit time. Discharge Q, so that's Q, capital Q. We'll see this when handling various types of heads and Bernoulli's principle and the continuity equation too. Okay, so that's discharge Q, is the volume per time. Density is mass per volume. Surface tension, force per unit length, is for kinematic viscosity, and this is dynamic viscosity. So you will see tables like this when reading and preparing for questions on fluid mechanics, but it's important that we're able to do what we just did before, which is given a physical quantity, given force, can I come up with the formula for force? From the formula, can I get a physical interpretation? Then you simplify it. Okay, so that means if you go mass times acceleration, you have to make sure to get the dimensions for acceleration, and then you end up with your dimensions, which you can cross-check and put into your formula table over here. So the whole idea of finding dimensions is a straightforward process, essentially, no matter how difficult it may look, because given this straight up right out of the bat, it may look like you have to do a bit of cramming, but you don't. You just have to remember discharge is volume per unit time. My kinematic viscosity is dynamic viscosity times density. My dynamic viscosity, I can get that from the shear formula. Okay, and so on and so forth. So once we're able to do this, we don't have to do any memorization of dimension tables. We just have to think of the formula, get the interpretation, simplify, and make our dimensions. Okay? So now to wrap things up, we're going to see if we can get ourselves the dimensions of these quantities listed here. Okay? So if you'd like to do this yourself, you can pause the video and skip over to the end to see whether you got it correctly. But if not, if you want to watch us walk through it, then you're more than welcome to stick around. So momentum, we know that momentum is mass times change in velocity. Okay, so we start with our formula, then we move on. Mass times are change in velocity. So whenever you're dealing with a change, so let's say I'm looking at displacement, for instance. Okay, displacement is, let's say, s2 minus s1, and these are both distances. So the dimension of a difference, or the dimension of a sum, because displacement is the difference between two positions, the dimension of a difference or a sum is the same as the dimensions of what is being subtracted or added. So if so let's say net energy is energy to E2 minus E1, the dimensions of net energy are still going to be the dimensions of E2 and E1, okay? It is one of the things that we'll come to understand when we deal with the homogeneity principle, okay? So since velocity is a difference of velocities, okay, dv is v2 minus v1. The units of dv is going to be the same as the units of v2, and it's going to be the same as the units of v1. So we'll come to understand this as we move on. So let's get from momentum. We have mass times a change in velocity, so that's going to be m, and remember velocity is a rate of change of distance with time, so that's going to be L raised to minus 1. So we can say that momentum is mlt raised to minus 1. Okay, work is force times distance, so work is force times distance. So force, set force is mass times acceleration. Okay, so let's go. So that's going to be m L t raised from -2 times, okay, then you bring distance down, times L, okay? So you have L raised to power 1 times L raised to power 1, and a lot of indices says we have to add these guys together. So that's ml squared t raised to power -2. For kinetic energy, so let's say energy kinetic is going to be half mv squared. Okay, so with constants, this is a number. So with constants, we can ignore this. Okay, you can ignore this. There are no dimensions to numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so forth. Pi, constants, gravitational constants, okay, multiplication factors do not have dimensions. So when dealing with dimensional analysis, we can ignore constants. So we're only looking at m and v squared. Okay, so m is mass, so that's m. V is velocity, so that's L t raised to power -1, and then we square this together. Okay, so that's going to end up being m L squared t raised to power -2, and we've been able to show inadvertently that kinetic energy is equivalent to work, dimensionally speaking. So these are one of the things that you come to enjoy when dealing with dimensional analysis. You can prove similitude, you can prove equivalence between two seemingly unrelated physical quantities. Okay, so these are the things you're able to enjoy when studying and dealing with dimensional analysis. Okay, we've been able to define it, look at the applications, look at where it's used, look at why we need it in the first place. Able to derive dimensions for quantities in tables, look at those, and even solve questions here. Okay, but on a side note, it's important to identify that in this video, we're going to be dealing with, and it's usually more common, we're going to be dealing with the MLT system, okay? So that's mass, length, time. In other cases, in very small, usually unique cases, you may see it as FLT, okay? The F here stands for force, okay? And remember the units for force is mass times acceleration, so that's ml t to the -2. So the reason for this is purely for laboratory purposes, experimental purposes. It's easier to measure the force of an object or the force on something as opposed to raw mass. But in this video, in most texts, in most literature, in most textbooks, you'll see them handling with the MLT system, which is what we're going to be using here. So it's important to know that before we move on. All right, so that's all there is to it when dealing with dimensional analysis. In the next video, we'll look at the principle of homogeneity and how we can use it to verify the validity of certain equations. Okay, so thanks for watching. I'll see you in the next video.